Okay, I guess it started. Who's saying the first words?
You do. You are welcome to start now.
All right. Okay. Thanks for coming by. Thanks if you're watching the recording on YouTube or whatever. So today, yeah, I'm going to give a presentation, a simple presentation on bidirectional type checking. And okay, let me start by kind of introducing myself. And at least that's basically to say that I'm kind of nobody and very unusual presenter on these seminars, because usually you have here people from academia and I'm totally from industry. And yeah, you can say I tried to convert from industry to the academia 2 times and failed. So I'm not presenting my research. Basically, what I'm doing is I'm giving kind of semi-tutorial or something basic, very beginner, hopefully friendly introduction to the bidirectional type checking. Okay. With that said, what is bidirectional type checking? Okay, first, yeah, the kind of definition or kind of description from Stack Overflow, Stack Exchange, Proof Assistant Second Change question. Yeah, the answer given by Tesla. Tesla was working on Arendt Proof Assistant together with JetBrains, obviously, for quite some time. I believe, again, having contributed into the implementation, so working with type checking, and yeah, I believe he knows a great deal about type checking and bidirectional in particular. Moreover, now, as far as I know, he's developing from scratch kind of his own proof assistant, again, heavily inspired by Arendt, called Aya. And indeed, I think this definition is pretty detailed and up to the point. I encourage you to revisit the definition after this presentation, and you might enjoy it even more. Still, on the other hand, it's pretty detailed and kind of close to implementation, so maybe we should have a step back and look at another definition from David Christensen and his tutorial. I'll have a reference in the end. So this is a technique that kind of transforms typing rules for a language into syntax-directed form. And syntax-directed basically means you have an algorithm. At every step of the type checking, you know what to do next. That's obviously an important useful property. And also, it promises to maintain close correspondence to the original presentation, original typing rules, but that's kind of a bit vague. So I guess we should go more concrete and look at the bidirectional or usual type checking, usual typing rules, and bidirectional form for simply typed lambda calculus. Simply typed lambda calculus, yeah, kind of at least one version is defined by this syntax and typing rules. I kind of throw booleans into the mix to have some ground type, right? And yeah, as long as we have booleans, we can have if then else. Usual stuff. Another particular thing is that for lambda terms, we have typing inside this term. Yeah, we type the parameters for the lambda terms. Okay, otherwise it's a pretty standard presentation, pretty standard syntax for simply typed lambda calculus, and I hope everyone can recognize it as that. So how do we type that? Again, pretty standard rules. Yeah, we immediately know that constants true and false are of type boolean, bool in this case. Yeah, we take variables or types for variables from the context gamma. If it's in context, okay, we know it's type. If it's not there, okay, it's untyped. or that the term is ill-typed anyways. So yeah, the rule for abstraction, yeah, you know, application, and for if then else, and again, obvious thing, condition have to be Boolean, and both branches have to be of the same time. We return this type. It's if expression, not if statement. We don't have statements here, only expressions, right? So in total, these rules define type in relation. Type in relation is like ternary relation. It has 3 parameters or arguments: context gamma, the term we're typing, and the type this term is supposed to have. Either has this type or doesn't have, right? Luckily, again, the simply typed lambda calculus typing is decidable, so we can simplify and say, okay, these are predicates, kind of mappings from these 3 things to booleans. That's true or false, that this term have this type in this context gamma. On the other hand, as every Prolog programmer knows, and I bet pretty much any function or logic programmer like Mini Conran, whatever, knows, oftentimes we regard some arguments of our predicates as inputs, and some, usually one, as output. Yeah, so we supply kind of the inputs to the predicate, and predicate kind of synthesizes, gives us this output value through unification and search and blah, 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 but still, we use predicates in kind of form of functions. Hopefully this is very familiar to all the practitioners, and I believe there are many people closely familiar with logic programming in the audience. And surprisingly, these kind of practical considerations have their counterpart in logic. They're called modes. So we have a positive mode for arguments and negative modes. Negative mode means, yeah, output. Positive mode means input. So how it works in logic? It works like this. Let's take an example for this rule for typing lambda abstraction. And we suppose that, yeah, we want to infer type, thus context gamma and the term we're typing are input, positive mode, are given as an input, and the resulting type we should produce as an output, it has this negative mode. So we are going bottom to top in our rules, usual thing. So we are given context gamma, yeah, the term, and the type, result type is unknown. So we go from bottom to top. Oh, yeah, I go bottom to the slides. But the kind of we propagate this known information from bottom to top, following these yellow, not circles, ovals, whatever, yellow highlight. So from this given term, we knew the variable name, the type of this variable. We kind of lifted up into context gamma. We knew the context gamma too, and we know the term. It's still here. It should be highlighted. We know this one. We don't know the type for this term. But according to our kind of induction hypothesis, at this point, we are able to infer this tau2. So after the next step, we kind of know tau2. And now we can propagate the information down and infer the desired type for this compound term. Yeah, we knew tau1 already, and we inferred tau2. So now we can construct arrow type from tau1, tau2. Easy enough, right? Yeah. Red is what we supposed to produce, and that's unknown, and moreover, it have to be unknown. Okay, I'll kind of talk about it again on this slide. Right, now let's check this application rule. Try to do the same with the application rule. Okay, again, we are given the context gamma, the terms T1 and T2. We are applying T1 to T2, so we know what we are doing. And we don't know the type of the whole thing. So we propagate the information up. And we, by induction hypothesis, now we can infer the type tau1 to tau2 from the term T1. Okay, yeah. Then we need to do something with this second term T2. And now, yeah, it's supposed to have, well, we're supposed to infer term tau1. So tau1 supposed to be kind of free variable in terms of like Prolog programming. But it's not free, it's bound. We already know what it should be. It should be tau1. We get it here. This kind of inductive step gave us both tau1 and tau2. So it's not free. We can't really infer it. It's already known. So it doesn't fit. I mean, okay, yeah, you can say, well, that's kind of technicality, and my Prolog implementation can go both ways. If it's given free variable, it will kind of infer it, unify, and if it's given already bound variable, yeah, not a problem. It will kind of work with that. Just check that it fits there. But still, kind of this exactly means that the predicate is not mode stable, kind of, or more mode correct. And it fails even funnier with the Boolean, with the if then else rule. Again, here we're not even having a variable. It's a constant, it's Boolean, it's constant. We know what it have to be, the term, what type it have to have. Then again, we have the same problem that after one step we will know tau, and the second one cannot infer the same thing. It can only check this. So what do we do with that? How do we circumvent this problem, this inconsistency? Any ideas from the audience? Again, the problem is that at sometimes, okay, this mode that we supply gamma and t term in and get out infer tau is okay, it works like here, but other times, yeah, we already know the type and we can't infer what we already know.
Well, you could split your inference function/relation into two parts. One will do check, where it will have some arguments and say true false. And another variant of your algorithm will be called inference, and it will synthesize the result from the inputs.
Yeah, exactly. I bet you know the answer beforehand, but yeah, that's exactly the solution.
I use it another way. I infer what I know anyway, and then I unify the result with what I know.
Well, that's basically the same solution. We split one predicate or one judgment into two judgments, one for inference and another one for unification or check or equality, whatever. The point is they have different modes. So one have these two positive modes, one negative. So it does inference, produce something, term type here. And another one have all the arguments in positive mode. So we have to give it all the necessary information, and it only checks that everything fits together. And with this, yeah, with these two predicates, we can fix our rules for application. Now we have bidirectional typing for application rule. We infer the type for the compound application, for the compound term application of T1 to T2. We infer as a premise type for first one, which is supposed to be have to be function type. But after we know it's a function type and we know the T1, tau1, we just check. This is kind of second predicate. We check because we know all these inputs, that everything fits, and then yeah, we can easily produce tau2 because we already know it. Yeah, we inferred that. We can kind of infer it again, return the result. And okay, it worked with.
In my room, there is a guy who doesn't understand the original problem and is afraid to ask, could you please repeat the original problem, why we introduced this bidirectional stuff, and what was wrong with original straightforward checking algorithm / intuition.
Yeah, okay. I didn't show like exactly that this just declarative system usual presentation for typing rules are not syntax driven. Yeah, exactly. Though, yeah, this presentation for this failure is kind of hints that, okay, it's not syntax driven. In particular, the fact that our predicate is not mode correct or mode stable. Sometimes we need inference, sometimes we need checking. What Prolog does, yeah, it means it's not syntax directed. At certain points we do one thing, like checking, and other points we do another thing, like inference, it's unification, and probably search through this derivation tree. Yeah, exactly. Prolog programs can intermix this stuff together kind of on purpose. That was the premise behind this logic programming, that, okay, it will search and find this stuff. But search is kind of not guaranteed and not might be time consuming. So we want exactly come up with functions that really kind of directly do the right thing from the start, not searching around if something will fit our specification, but our specification is specific enough to say kind of just do this thing, then do this thing. If this fails, it certainly fails. The term definitely ill-typed. If it works, then here is the type. So we're kind of turning this logic style declarative type system into algorithmic one. Kind of we write the rules that look like logical rules, but they're constrained enough to be actually algorithmic or specifying particular algorithm. So at every step we know what exactly to do.
There are cases where using the initial rules in one and other mode produce different results.
No, not necessarily different results.
Or different outcome.
I don't think, yeah, not for simply type lambda calculus for sure. It's too simple, and kind of we're always gonna end up with one and the same type for any given term. Though kind of the algorithmic steps along the way might be different, right? So we might venture into some unfruitful directions, like take the wrong turn, look there, understand that, okay, it doesn't match, take another branch, and finally found the solution. We want to avoid this wandering around along the search tree. We want to directly go into the direction of the right solution at every step.
So in this concrete case, we are given the type of the function. We can't infer it here.
Yeah, we already know tau1 from here.
So
Again, if we're kind of sticking with this inference thing, yeah, another option is to introduce here another variable and then kind of introduce another constraint that this one should equal to that one. But that means we are starting searching. This thing might produce several. In principle, it might produce several outputs, right? And then we filter on them until we find the right one that equals to this one here. So this is part that might go into search. And we want to avoid that because we already know what we are looking for and we want to just kind of check that, yeah, it's there.
Well, yes, if the type checker contains possibilities to roll back to produce more than one result for one given term. Otherwise, it will just fail with an error, I believe.
Yep. But this backtracking is exactly what we want to avoid. This is syntax-directed means. We never backtrack. We always know where to go. And it's the right direction. If it fails, then it will fail for all other possible approaches. And we never kind of wander around. So we're going there. And this mode correctness is one step in the right direction, or kind of major step in the right direction. Thus, okay.
Does that mean it will require more annotation? Like the Haskell's apply operator? Shouldn't it require
Let's not kind of get ahead ourselves.
Okay.
Yeah. We'll see. We'll discuss it like in a half a minute. Going back to the abstraction rule, type in abstraction, we already kind of checked that it's mode correct, so we can kind of present it as an inference rule, and it will work. We already checked. Okay, it works, right? So, okay. On the other hand, yeah, in practice, oftentimes or kind of canonical way is to have it as a check-in rule. We are checking that particular lambda term have given type, and yeah, in the premise of this rule, we are again checking that that the term have the known type, because okay, we know from here what it's supposed to be, and yet tau1 we know too. Well, at least one kind of advantage of this form is that we can drop this extra type in annotation here. If we know tau1 from here, we don't need to carry it here. We still can construct x of type tau1 to extend our context from this one. Okay, and why it's recommended and often taken in the form of a check-in rule have two sides. One is theoretical, another one is practical. Let's start with practical considerations, right? Again, kind of going back to Haskell, oftentimes we would like to have our functions checked. We would like to, or even force the user to provide these type annotations for at least top-level functions, because it localizes errors, it provides a form of documentation, and, well, other kind of nice properties, and yeah, we can drop the annotations on the arguments. So, well, that kind of practical consideration, though they're kind of guidelines and nice to have things, not necessarily a must or commandment. The theoretical argument goes like this. This is essentially, or not essentially, kind of by definition, this is introduction form in the sense of logic rules, you know, introduction rules and elimination rules. The previous one was that one was elimination rule for arrow, right? And this one is an introduction rule for an error. And generally, yeah, we synthesize types for elimination rules and check types for introduction rules, because we can't always synthesize for introduction rules. In this case of this style rule for lambdas, we can sometimes if we carry type annotation on argument. But in general, say the simplest case is sum types, right? Like either A or B, yeah, or sum A plus B. We have introduction like in L, left introduction, and introduces value of type tau into type tau plus sigma. And what is sigma? We can't possibly know. So we don't know what type to synthesize. But if we are given type tau plus sigma, we can check that, yeah, indeed, this thing, the term that we given, that we inject in, checks against tau or checks against sigma in the case of right introduction. Following the same direction, we use checking for the lambda introduction. On yet another hand, in principle, nothing prevents us from having like both checking and inference rules, like both forms of lambda with type annotation and without, and checking rule for lambda without annotation and inference rule for lambda with annotation. Or even all three forms, and a checking for this form, and both inference and checking for annotated lambda terms. And more than that, yeah, there is a presentation, and actually in the seminal paper, local type inference by Pierce and someone, I forgot the second author, I'm sorry, but they had all three rules there for reasons. So it's possible to go like all these ways. All right, now, yeah, okay, what's this? The next. Yeah. Actually, yeah, there was another problem with this rule, with this one. Yeah, we're supposed to check against this type, but where are we going to get this type? So we have to tweak syntax a little bit. And the major addition is this one. We're adding annotation like as a separate term. That is kind of new sort of lambda terms. Term T annotated with type tau. And along the way, I dropped this type annotation on lambda. So this is our variation on lambda calculus for bidirectional typing. And here is the set of rules, modified rules for this new shiny bidirectionally typable lambda calculus. Apart from a couple problems, what's missing? You should feel something is missing on this slide.
Like lambdas introduction?
No, introduction is here.
Okay.
Here is elimination, also known as application. Here is our rule for if then else. It always checks everything. It checks the conclusion and it checks all the premise against null types, obviously.
We still have type annotation on lambdas here.
Nope. It's x.t and t is term and all my types are taus.
Well, but in the premise of the BTApps, x is given type. Where do we get it?
from here, it's checking rule. So we are given type tau1 to tau2. We split it into halves, obviously, and one half goes here. We attach it to x, and the second part goes here. We check t against tau2, and we know
it works
both
in
things from here.
in the reverse direction. We are given the part below, and we infer the part above. Okay, we check the part above from the part below. Yes.
Yeah.
Okay.
In type inference, we always go, well, actually in proof inference or kind of proving, we go from bottom to up to top, from bottom to top, from conclusion to premises. So that's usual stuff, and actually I explained that already. What? Any
We're
other ideas about what's
we're-
missing?
We're missing ways to link two directions together.
Yeah. Well, before that, okay, the obvious problem, and one part of this link is that there is no rule for type annotation itself. We have type annotation in syntax already, but I haven't written down the rule for that. Another thing, again, here for true and false constants, I went for inference rule, which is, again, kind of against this guideline. I outlined its introduction rule, but I'm inferring. On the other hand, well, for true and false constants, you for sure can infer that it's Boolean, right? But still, in this rule, I state that it should check against bool, and we can't even check constants against bool because we only have inference rules for them. Luckily, yeah, we can switch between one direction and the other. And in one direction, it's exactly annotation rule. If we have annotation of type tau for term t, yeah, we can synthesize type of this thing. It's tau. Yeah, for sure. We know we're just returning the same tau we were given in the first place. But to be sound, we check that, yeah, indeed the term have this type that user said it should have. Otherwise, yeah, system becomes unsound. Just for that. Just to be sure, we check it.
Sorry
Yeah,
to
now the
interrupt
question.
you. I just understood that the place where your mouse is not.
Not visible.
No. It's look. It's like offset. Like, please point on BT annotation, the center of the text.
Yeah,
For the
like
mouse.
here.
It appears right above the modus ponens of BTN right now.
Well, yeah. Another problem is that yeah, this the pointer disappears on this.
Yeah.
If I leave it in place, it disappears for me at all. So yeah, I'm sorry. Technology, you know. And yeah, well, I can't point with my hands. I don't know. Somehow we have to. You have to guess. Yeah, I'll kind of wave the pointer somewhere around where I intend, and yeah, you have to get. So the second rule is just kind of switching the directions. Yeah, in the sense, okay, if we given type tau and t and yeah everything, and tau t synthesizes type tau, then we can check that, yeah, we can say that, yeah, we checked. Like checking in this case consists of just synthesizing and then seeing if it's the right type. If it's the right type, then yeah, we checked. And what's problem with this rule? It has one tiny problem again.
Is it possible to somehow loop in this case?
No, nah. Simpler problem. Our favorite problem. It's not mode correct. We can synthesize a term or type tau, we already know we have to synthesize a new one and then check separately that, yeah, they are the same. On one hand, it kind of undermines somewhat the whole kind of construction, because, okay, we could introduce this checking equality check into the rules we had before. On the other hand, well, actually it corresponds pretty, how to say, closely to the actual implementation in the code. Because in the code, when we synthesize it, we're supposed to assign this result to some variable and then check that the contents on one variable equals to the contents of another one. And yeah, our equality relation have both arguments in mode, positive mode plus positive mode. And this constitutes the bidirectional rules for simply typed lambda calculus with bools and if then else. I'm pretty sure it's complete presentation. Any kind of questions about this theoretical part?
I have a question about BT annotation rule, about colon sign. I didn't get it. What does it mean in BT annotation?
The colon in this colon is just syntax, literal syntax for annotation.
No, not column. The colon sign. Double dots.
Yeah, it's literal syntax. We have this syntax here in the syntax.
But in rules it appears only in the bottom of BT annotation or when you put something in context.
Okay, in context, the human level meaning is the same, but technically, okay, they're not related. This is object level syntax, literal object level syntax. Yeah, especially this double colon. It's supposed to be there in your syntax. It's what you write in your editor, like double colon, well, some term on the left, double colon, type expression on the right. And here it's obviously part of a meta language, but the meaning is the same. It connects term to type.
Yeah,
in this case, it only connects variables.
I mean, I don't see any place this colon sign can come from only in BT annotation.
It is given. We are starting from this syntax.
It comes from the program. You write your program in text editor, presumably. It's like this annotation, double colon annotation in Haskell.
But okay, if you write the annotation in STLC, when you write your program, you don't have any problems with inference. You can check all types.
If you annotate everything, then yeah, you only need to check. But the point is that we can annotate some terms and not others, and then we check some terms, but infer types for those that were not annotated.
Okay.
Again,
which terms?
Let me point out that in this calculus, you can't annotate variables in lambda terms. You can't put double colon here.
Okay.
You can only annotate the whole term with a type. You can stick it there in the variable, between variable and the body. Thus, again, you have to write it this thing like that, and then double colon and that type, and then we check the whole thing. Well, I don't know what to say more about that. We will see an example in the code, in the implementation. Yeah, maybe that will
So
illustrate
the
anything.
the BT check rule is saying like if we cannot check something, we have to annotate it. It
Check
is like
no.
a fallback.
It says basically this thing. Okay, we have to check that T1 is of type bool. But if T1 is true, we don't have check-in rule for that, but it has inference rule, so we can apply inference rule, kind of confirm that, yeah, the inferred bool equals to the required bool and say, okay, it's done. We checked that the term have the type Boolean.
So it is checking falling back to inference. Basically.
Yep.
Okay.
Again, these two rules, annotation and check-in rule, switch between these directions. One goes from inference to check-in, or kind of reduces inference to check-in. The other one reduces check-in to inference. That makes these functions mutually recursive, or predicates, if you will, mutually recursive. Though we will write it, these predicates or judgments, as functions, because that was the idea behind bidirectionality, to make it syntax driven and make it into functions. Other questions? Like 3, 2, 1. Okay, then let's go to the functions. Yeah, I did implement this simple system over a weekend. Sorry, I know that in this community the OCaml language is preferable. I had a thought that maybe I'll do it in OCaml, but then I dropped that and did in Link 4. On the other hand, I'm aimed using no dependent types. These plain simple kind of non-dependent, usual types. So it's essentially the same as OCaml code, or even simpler than OCaml, just ML code. Yeah, I define a kind of synonym name for naming these variables, which are, in a sense, actually numbers, natural numbers. So I just number all the variables, though it's not de Bruijn indices. It's not indices, it's like names like strings, but numbers. Okay. Then we have our types, Boolean types and functions, which have kind of type A to type B. Equality, obviously, Booleans equal to one another, functions equal if they take the same types to the same types. Everything else is unequal. Type class instance, whatever, terms, exactly, variables, referent variables by name, application of one term to another term, abstraction over some name in some term. This term is kind of open, it can have variables inside them and refer to this name. Terms true, false, if then else, which is key condition then else. Annotation of term with some type. And we define constants or contexts. Contexts, gammas, which are lists of name type pairs. Simple enough, right? Like everyone understands that this is the exact same lambda calculus in code.
I wonder only where type variables.
We don't have type variables. It's simply type lambda calculus.
Okay.
We only have ground types, bool and functions, between bools and functions of bools, whatever. No type variables. Super simple. And these are these two functions, mutually recursive check and synthesize functions, which go by the book, by the rules. we take in checking takes in context gamma, term t, type tau, and returns bool whether everything matches or not. And yeah, we have rules for checking abstraction. Remember lambda terms. Yeah, we check that the type we're given is a function type. If not, yeah, it's totally ill-typed. If it's function, we check that, well, we extend the context gamma, obviously, with this pair. We know type T1 from whatever was given. Yeah. Check this type, subterm T1 in this extended context against type tau2, whatever was written in the rules. The same for if then else. We just check the three subterms. Yeah, the first one against bool, we know it has to be bool. Others against given type tau. Whatever we given, yeah, they're supposed to check, both check against exactly that type. In any other case, we apply this rule for switching directions. So we try to infer type. In the same context gamma, we try to infer some type, kind of any type for this term t. If we get some, we check that they're the same type, that indeed it has the required type. In any other case, we return false that didn't match. And synthesis, again, pretty straightforward. For variables, we just look up variable in the context. If it's there, we return the type it has. Thus, we return optional type, it's either known or some type that we inferred. Yeah, application rule. Again, synthesize function type. It has to be function type. We match that it's function. Otherwise, it won't work. If we get function type, then okay, we again split it into these two things and check that the second term have the right type, have a type of the argument. In that case, we produce the tau2 as a type of the resulting expression. Otherwise, it didn't check. For true and false, we synthesize bool. We know from the doorstep that what it is. For annotation, again, we just switch directions. We check that the thing have the provided type, the type of annotation. If it does, we return exactly the same type. Otherwise, it isn't checked. And yeah, in every other case, we don't know what to do. It didn't work. We don't have rules for any other cases. Like, was that straightforward? Wasn't it?
Kinda, yes, but I see that we check introduction of lambdas and the elimination of booleans, which is funny. Also, we check also we synthesize elimination of lambdas and introduction of booleans.
Yeah, like... that was exactly the rules I presented.
Okay, then.
And already I kind of discussed that, yeah, following the guideline, we would have check-in rule here, but realistically, we can infer it. Yes. And again, this rule for switching directions allows us to go from one to another easily. Thus, the code directly follows the rules.
Okay.
These bidirectional rules, indeed, completely algorithmical. They're syntax driven. We match on the syntax, and in every case, we know exactly what to do, what to check, or what to synthesize. If it goes, it goes. If it fails, we know for sure that it won't work any other way anyways. All right. So this was simple enough, right? Any other questions? Kirill?
No, I wanted to say this was simple enough. Now let's go to F omega.
Go where?
Go F omega or something. more
No,
powerful.
not that fast. Okay, let's first discuss this technical, another technical thing. Yeah, like it is well known that bidirectional typing rules are better for producing meaningful, more kind of localized errors. So how do we inject errors here? Because this thing does not tell anything about errors. If it fails for some reason, and you have no idea why. Yeah, we check equality, and what? So what? Yeah, we check equality here. I guess that's the only place we check equality, and it's just usual Boolean equality. What was the questions? Yeah, in this presentation, it's decidable. Again, here the decision procedure, so to say. Well, it's kind of obvious. Okay. I want to demonstrate that, yeah, that this does check the types for terms. And yeah, like here, how it's supposed to look in more or less kind of syntax. Yeah, we have an expression here, then the colon that's literally colon from our syntax, and the type that this thing should have on the right here. So we supply into functions and the value, Boolean value, and we apply these functions one after another to the value, and obviously it should have this type. And as I mentioned, yeah, I encode the names for variables with numbers. They should be just decent numbers, and any numbers will go in any order or without order. The body is an yeah, 3 abstractions, and then applications, 2 applications inside the body, referring to variables introduced by the abstractions, obviously. So the type, yeah, I introduced the short form for the name for this type from bool to bool, for functions from bool to bool, and then the type for the whole thing, which is again function type. Function types associate to the right, so it's a function like this one function from here to there to that whole thing. So Boolean to a function from Boolean to Booleans to a function from Boolean to Boolean. And our example in general is annotation of this term with this type, and so we write it like this, and then we try to synthesize a type for this term, right? And like, yeah, it synthesizes the type, which is exactly the same type we provided, but that's how we coded synthesis for this annotation type. It have to return the same type, exactly the same type, but in the process it checked that term we given really conforms to this type. In the code we really call this check function on this type, so yeah, indeed everything fits together. Not overly excited, so okay, let's go to errors. Yeah, to produce errors we have to change the result type, and this result is just a type I define. It's a sum type of strings and something, in this case unit, because if we produce the right side of this sum type, then okay, it did check. Otherwise we would produce left hand side with an error message. Like here we produce left value with some message about wrong type, and this function just produces string out of term and type. Yeah, because we have more complicated types, we can connect them with just Boolean and Boolean conjunction. So I implemented a function to kind of check the, basically monadic thing. Whatever. Again, in case, yeah, now we check the types for equality, and if they match, we produce right type, right unit, whatever. In other case, we produce again the error message that types were incompatible, and here I provide the term, one type, and another type, like the type we were expecting and the actual type that this thing inferred for the term. Thus, one of these advantages when we have both checking and synthesis, sometimes, yeah, we have both types. We know what it should have been, what was expected, and what it actually is. And we can report both types that, okay, this type term you provided in reality have this type, while another type was expected. Yeah, here we just, how to say, reinsert errors from synthesis into checking, because the right-hand side is different. Synthesis, well, here you see, synthesis returns S type, and the checking just have unit here, so we have to reinsert errors, and in this fashion we, how to say, propagate errors from within terms to the outer terms, because our check-in synthesis goes kind of from outer terms into inner terms. If there is an error check-in inner term, we kind of propagate it back. So we have, again, more localized errors, which is a good thing. Undeniably a good thing. Again, produce an error like unknown variable. And I believe, no, we don't know the type that it should have, but yeah, we know that it's supposed to be a variable, but it wasn't there. Okay, unknown, unbound variable in this case, whatever, I'm sorry. Then again, propagating errors on couple occasions. Here we checking and returning the type that we know. Yeah, another case when we have an error. I mean, we kind of know what error we have. It's supposed to be a function type, but apparently it wasn't, so we can report it there as such, that exactly we were expecting a function. And yeah, general error that if somehow user manages to supply a term that we don't know what it is, like it's some weird form that we even don't have rules, I don't think it can ever happen. Should be total, but yeah. I didn't want to prove to lean forward that these mutually recursive functions are total, so I said they're partial, and I said, yeah, plug this, catch everything, case branch, what close there. Okay. And now it rules, or it works kind of like this. Yeah, if we purposefully kind of put a wrong type on the same term, forget that it's supposed to have a, well, basically I missed one boolean here, so it says that, yeah, this term was checked again type bool already, but yeah, obviously it's not a boolean, so we can infer that, yeah, I forgot a function type at least somewhere there. Another thing, obvious thing to do is we have gamma. At any point where we report an error, we have this context gamma with all the bindings we already encountered in there, so we can spit out all these like relevant bindings, like this have this type, this variable has this type, so it will say something at least about these variables 2 and 1, that they have particular types. I just didn't implement that. The possibility is there because we have this information. Okay, how was that?
That was fine. At first, I was concerned that the term is quite big, but then I remembered that it's a function literal checked against a boolean, so it has to stop right here.
Yeah, exactly. Okay, another well-known kind of property or claim about this bidirectional type system is that they're extensible. In particular, that they're kind of easily extensible for subtyping relations among the types. So how do we do that? Let's take as an example the simplest, most kind of straightforward subtyping, boring one. I left the syntax of the terms as it was, exactly as it was. I just add integer and float types there, and we will have subtyping relation between ints and floats like this. So, well, a subtyping relation has to be reflexive. But apart from that, we have that int is a subtype of float in our system. And for sake of completeness and kind of future proofness, we have this relation. I mean, the rule that subtyping relation is transitive, which makes sense, right? It's supposed to be transitive, so we have to have a rule like that that states that it's transitive. Again, what's the problem with this rule?
That the sigma is not known.
Yeah, and what problem it poses?
That there can be a lot of variance for that sigma to be.
Yeah, well, that one thing, like,
And
yeah, it's not syntax directed in any way. The other thing,
since it is transitive, it can like exponentially explode in variance.
Yeah, there is such a possibility. Another thing is that it's problematic again with respect to modes. It can have both arguments as a positive mode as inputs. Otherwise, yeah, sigma is unknown. We can't supply it here as a known thing because it's unknown. It's free variable essentially. Yeah, either here or there, or both ways. If we kind of regard tau as an input and rho as an output, that kind of technically fits. I mean, here rho is unbound. Yeah, then we go here and sigma is unbound and we infer it. Here sigma is already bound. We can infer rho and then we propagate it here. On the other hand, it makes totally no sense computationally because if we're inferring rho from tau, why we infer some sigma from tau and from sigma we infer something else and not why can't we infer rho in one step if we are inferring anything? Why, how possibly this thing can produce something different from this thing? So it's mixed up. Either it's mode incorrect or it makes no computational sense. Thus, we introduce another relation, slightly different relation, different subtyping relation, which is again reflexive. And yeah, it's kind of easy to extend our bidirectional system with that rule because remember we had a rule like this. Here it was checking for equality of the types. This sigma and tau supposed to be the same type exactly. And we generalize it to this relation. And now, bam, we sticked the subtyping relation into our directional type system, altering only single rule. Cool, huh? Is that enough?
So we check in this rule that T has the type sigma, basically. And then we infer...
Tau is subtype of sigma. We are Okay, we're checking, yeah, type tau against sigma. And modes
So
for this is that, yeah, both are input modes.
So we infer tau and check that tau is a subtype of sigma, basically, yes?
Yep.
Okay.
And here everything is mode correct. Yeah, for that we know, again, this relation now have both arguments in plus mode, positive mode or input mode. Okay, but it's not exactly enough because we have, apart from these ones, we have another type former, namely arrow type. So we have to explicitly provide this relation for arrow type form. And yeah, this is kind of expected rule with covariance in arguments and I mean contravariance in arguments, covariance in the right hand side. The downside is that now we have to provide rules like that for all our type constructors. Like if we have product types, we have to provide this rule, such a rule for product type products. Another one for sums. If we introduce another type constructor, we will have to cover that. And we have to kind of cover all that separately. On the bright side, we get the system that's still syntax directed. And yeah, we can prove that this relation is complete with respect to that relation and with respect to this rule. So it's in essence transitive, though it's kind of explicitly transitive. We write down all this transitivity explicitly. That's an unfortunate, but on the bright side, we preserve algorithmicity, kind of this syntax-driven system.
I have a question.
Be my guest.
We at some point might want to introduce like type variables and rank 1 functions and parameterize types. Would we to annotate the parameters of them with core contravariants, like invariant, contravariant, covariant, and phantom?
Wow. Oh. Actually, I don't know. At this point, I have no idea.
Because if you are declaring a type constructor like list of A, you can't know if the A is maybe a predicate from A to B. In this case, A
No,
is
I know.
contravariant.
Yeah, the problem where it arises. I guess that, yeah, heavily depends on the system, what types you have there, what constructors you have there.
Like, for instance, if A is a subtype of B, then list of A is a subtype of list of B. But if we have A subtype of B, but we use predicate constructor, then predicate of B is a subtype of predicate of A.
Yeah, I
So
mean, I know where these problems arise. Yeah, I don't know. I have no idea. I haven't seen such a system, though I didn't look too deep into the woods. Yeah. Well, what's there? I wanted to mention some other extensions I at least heard about. So when we have a subtyping in our system, yeah, obvious. Next step is have structural subtyping. So there are I guess there are bidirectional type checking disciplines or systems for structural subtyping. Yeah, definitely union types and intersection types are covered. Yeah, we can stick generalized algebraic data types there, confinement types, and even dependent types. More than that, basically bidirectional typing discipline is the major form of typing for dependent types, and I guess the only form where we can infer at least something, where we can meaningfully infer any types. though, yeah, can't tell you much about these developments. And yeah, they're not as simple as the ones I showed you this far. Yeah, when we kind of throw more complicated types, more complicated construction to the mix, the system grows bigger and heavier. That's true. Kind of no free lunch. Any other questions along the way? Maybe more.
It's kind of weird that you silently avoid avoid to extend your system by polymorphism, which is an obvious extension.
Okay, I'll talk about that a little bit later, kind of a bit after the main thing. So yeah, I have. This is basically the last kind of meaningful slide, or kind of informative slide was discussing. Yeah, again, I mentioned that when we were discussing these typing rules for lambda terms, the introduction rules for function types, that yeah, you can have it this way as an inference rule, you can have it as a check-in rule, or you can have all of them in your system in principle, and it doesn't break the system. That's possible, and that was done in practice. So what are the guidelines for either choosing better bidirectional type system among some possibilities? Like you survey literature, you see several type systems slightly different for essentially the same thing, and you think what's better, or like guidelines to produce better one yourself, better suited for your particular case. And okay, particular authors, I'll give a reference over one slide. So just these 4 criteria. Well, mode correctness we basically discussed throughout the whole presentation. Yeah, I presented mode correctness as a motivation, kind of driving force and major criteria in making the system bidirectional. Though it's kind of necessary criteria, but not sufficient. You can totally have mode correct, but not syntax directed system. Still, I claim that you can have syntax directed systems that are not mode correct. So mode correct is very important, and I guess it kind of cuts very many branches that are not syntax directed altogether. So it's kind of powerful guideline into the right direction. Then, yeah, again, obviously your system should be complete or have to be complete. You have to have rules for all your syntactic elements, right? You have to check or infer somehow, produce the types for all the same terms that kind of not bidirectional, this just declarative system can type, all right? Then again, yeah, size, our favorite criteria. The fewer the rules, supposedly the better. At least if you want to prove anything about your system. More often than not, fewer types, kind of easier to cover with proofs. Well, that's kind of rule of thumb. Again, that's not a law of the universe. There are exceptions. Yes, sometimes kind of having more types, maybe simpler or detailed types, is the proof burden. On the other hand, yeah, usually size matters. And then again, kind of more practical guideline or criteria is annotation character, and that's pretty subjective and pretty complicated. Again, these authors divide it into 4 characteristics. like how lightweight are annotations, so how many annotations you have to put there for the system to work. Again, it's not a precise thing, but the fewer the better, right? Then the annotations should be stable in the sense that, yeah, changing kind of bits locally shouldn't have profound effects on completely unrelated parts of your program, right? What are the two? Stable, kind of legible, yeah. We would like to kind of easily understand what needs to be annotated, what need not, why it needs to be annotated, the things that need these annotations, though that's totally subjective. That's very kind of vague criteria. I guess I totally forgot the first one, though I encourage you to check the reference. But, no, we start with the references again. The major sources for this presentation are these two: Frank Pennin's lecture notes and David Christensen's tutorial on bidirectional type checking for this simply type lambda calculus with booleans. And yeah, Pennin was discussing this subtyping relation in particular. And there is a survey, yeah, due to Krishnaswamy and Dunfield. The criteria is from this survey, so they discuss this criteria, they discuss kind of this classical recipe, again, due to Pennin, and they at least overview many or a number of extensions to bidirectional type checking. In particular, they discuss this bidirectional type checking system for polymorphic lambda calculus, but the one with what is higher candidate types. Yeah, and that's pretty hairy, actually. So before venturing into this, discussing that, references to the code, the actual implementation ID lives by this address. Then there are many more implementations due to Alexander Gryzlov. And yeah, he mostly discusses what is reduction rules, kind of machines to evaluate lambda terms in number of systems and extensions of lambda calculus. But there are, well, major thing is intrinsically typed, and this code is an interest, though there is kind of extrinsically typed lambda calculus, at least one implementation there, so you can check and contrast if you like Idris. Another major source for all kinds, well, several kinds of systems is programming languages due to Andrei Bauer. Yeah. Apart from untyped and object-oriented languages, there he has, I guess, 3 functional languages. One lazy, kind of Haskell-like, with in-the-mirror type and discipline, I believe. So you can compare that, and the other 2 are eagerly evaluated, and I believe either bidirectionally typed or something very close to that. Anyway, you can study the implementations and compare the approaches, compare the error reporting. And if you're going into direction of dependent types, then there is again elaboration zoo due to Andreas Kovac. I don't know how to pronounce his second name, unfortunately. There you can find kind of step-by-step several kind of stages of more and more sophisticated dependently typed languages with more advanced type systems and elaboration systems. And I believe that's mainly bidirectionally typed, but like all the way to dependent types. So very powerful, but much more complicated thing. Wow, that's basically it.
Can I
At
have
least-
one unrelated question? Does rank one and rank n types introduce subtyping into the language? So is
Could you
the
please repeat? I didn't hear.
do the
heard it.
rank one and rank n types introduce subtyping into the language? For if you have a function of
Not
type
even that. Actually,
int.
parametricity introduces subtyping.
Okay. So int to int is basically a subtype of for all a to a.
Sure. Yeah.
Okay.
Yeah. So that's already part of even Hindley-Milner type inference system. Like any other questions about this? Yeah, the presentation, what I was talking about, kind of more directly. I know that this thing is nearing the end in the terms of the type. Yeah, there is a comment in the chat that actually function for all a from a to a is a subtype of int to int. Yeah, for obvious reasons, as well as subtype of string to string or whatever. Yeah, it's more general type, thus it's subtype of more concrete types. Yeah, if anybody have some steam left, I have a couple extra slides about Hindley-Milner, but kind of more hand-wavy, and that's kind of extracurricular.
Well, I'm interested.
Yeah. And if anybody have questions about the main part of the talk, better we address those first and then move to this, yeah, more hairy stuff. So another last chance to ask the question about the simpler stuff, simply typed bidirectional typing. Going 3, going 2, going 1. All right, now to hairy stuff, right? Yeah, first, again, let's go back to this question, system F or not. In particular, high-kinded types or not. So the remark is that traditional classical Hindley-Milner system does not support that. It supports only limited form of parametricity, namely prefix parametricity, I believe. Parametricity, whatever. So all the quantifiers for all quantifiers have to be on the left side and quantify all the variables in the function. So you can't have this universally quantified function itself as an argument. Well, probably everybody knows that. One technical consequence of this discipline is that actually we don't have these quantifiers on the level of types. We divide our types into 2 levels: the types and the schemes, or schemas, whatever. And these schemas, type our functions, parametric function, they have this for all quantification on the level of schemas, but inside this schema there is only type that only can have pre-variables or kind of simpler types, the actual types. And I don't know, I never found a bidirectional type system for this kind of system. I don't know, maybe they decided that why bother with this, how to say, more a bit contrived, but simplified, limited form of parametricity. Let's bite the bullet and implement already for full parametric system with these high-kinded types. The kind of downside is that, yeah, with these high kind of types, the typing system becomes pretty hairy. Again, you can read about that in Dunfield and Krishnaswamy. Actually, two papers. First, they wrote a paper, early paper, presenting such a system. Basically, there are even two versions of a bidirectional typing system for this parametric with high kind of types system there. And then in this survey, they kind of explain their previous paper, like what is going on there, what was going on there. It's not simple, okay? Pretty complicated stuff. But this is a presentation, like declarative presentation for this typing for this prefix typing system due to Hindley-Milner. Okay. Again, yeah, variables are as per usual. Application, again, yeah, totally as per usual. Abstraction, here even without explicit annotation on variables, somehow we're supposed to get the right type or guess the right type for the variable in this. To stick it here, anyway, somehow it's supposed to work. They have let binding there. So again, pretty much the same kind of typing for the let binding. Then, yeah, instantiation rule, which again appreciates kind of or admits this subtyping relation between our types when we have this polymorphic types. Polymorphism, not parametricity, polymorphism, sorry. Which we discussed. And then, yeah, the generalization rule, how we type essentially schemas with for all quantifier. Yeah, and we require that it's not free in gamma. Usual, again, thing. Then there is classical algorithm W for this system, like algorithm. Thus, as an algorithm, it's again syntax driven. It's not bidirectional, but as an algorithm, it's still syntax driven. It looks like this. Kind of looks scary. On the other hand, they just explicitly tell you what to do with the substitutions. This as 0 as things are substitutions. And if you know logic programming, you know what a substitution. Yeah, when we unify, get substitution out of it, we can apply substitution to terms, which maps free variables to either other free variables in general or kind of some ground terms. And here, yeah, this algorithm, apart from inferent term type of a term, produces or infers a substitution. For variables, yeah, it gets the type from the context essentially, though it instantiates somehow the type, more general type into ground type, and produces empty substitution. Then we work from there and kind of construct more sophisticated substitutions, basically applying substitution to a substitution. Well, you know, essentially it's a function composition on substitutions because they're functions. Yeah, what's the question?
I don't see they ever generalize things. They only instantiate, I believe. Shouldn't they generalize the body of let? Like no body?
Probably this bar actually means they generalize or something.
Okay.
It's a weird thing. I didn't really didn't put enough time into studying the thing, and from kind of look over the Wikipedia page, I didn't quite get what this bar thing is. Anyway, yeah, they have a unification here, most general unifier, multiplication between terms, applying substitution, blah, 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 applying substitution everywhere, producing new variables, free variables, right? And unifying, stuff like that. So it's not that complicated, right? Though it's complicated. On the other hand, yeah, huge part of these complicated presentations come from this fact that it's detailed and tells you exactly what to do with substitution, well, basically guiding you by the hand and telling you what exactly to do in every single case. Thus, it corresponds directly to an algorithm and it's syntax driven. So comparatively not that complicated thing. On the other hand, for comparison, I decided to include bidirectional type system for dependently typed language, which looks like much more obvious, right? Yeah, the same rule for notation, like one of my favorites, obviously, yeah, which switches the directions one way. Another, again, rule for conversion, or okay, we are switching directions other way around from checking to inference. Here, one complication is that now we have to check the equality between types, terms, types, doesn't matter here, in a context or in the context gamma, because our types can have variables in them. Yeah, so we have to provide a context and check equality in that context. That complicates things a bit. Yeah, what's the question?
I don't understand what to do if we have to unify two types and there are neutral terms in it, like a variable.
We have to unify two types and what
We have
then?
to unify two types and there are like projections inside those types, like
What? Transaction? What?
Projections.
Projections.
Like we are calling unknown function inside the type. What do we do?
Why projections are unknown?
Like the result determines the outcoming type. Like we have to unify fx and jy, and they might end with the same type, but they might not.
Well, actually, I think the answer is we don't have unknown functions there. One thing, again, about dependent type theory is that we reduce the terms, the types, we reduce the types to we can evaluate. Well, we normalize them. They call it normalization. In particular, they normalize by evaluation, but that's a technicality. So we evaluate, reduce functions inside types. Thus, we don't have unknown functions there, and known functions we reduce. Either they kind of reduce to the same normal form, or in the end, the same normal form. In which case, yeah, they are compared to equality and kind of much. Otherwise, they don't. And even if we kind of throw kind of uninterpreted symbols, functions into the mix, into our type theory, yeah, now we have to provide reduction rules for them, just like in the system declaratively that, okay, this thing reduces like this into this value, and then we can evaluate them.
We still can end with a neutral term inside what we unify. We can like wrap both sides we unify with an introduction, like a lambda. So now we have to unify the expressions inside the lambda, and they can have unknown things, which were the arguments.
Well, I don't think we can hit this problem in this particular presentation because this one is super simple, super limited. It's not really dependent, even not for real dependent on values, kind of half dependent system, because we don't have even identity type here and no inductive type, so we can't inject real values into the types. Anyway, for kind of real dependent type systems, this unification and normalization of open terms is a problem, is a challenge. I can't tell you out of my head how people solve that. Somehow, they solve, but probably there is still no single best solution. It's kind of a problem and challenge. So anyway, again, for this kind of limited dependent type system, though it's parametric, it's already parametric because, well, our types are values and we have lambdas over values, so we can use them in the level of types. So kind of just naturally our system becomes parametric. The typing discipline is plain simple, and even we can infer some types, like meaningful types, meaningful inference, like in the case of application, lambda or arrow elimination rule. We infer the type, and by the way, we reduce inside this type along the way, thus getting kind of new type. Well, other inference rules are pretty straightforward. Though again, inference rule for arrow is not that trivial, so we kind of inferring, well, or performing, well, somewhat non-trivial inference and some checking along the way. So that's kind of.
That's not quite a simple system because I see that it tries to like lift universes in the I star and I arrow rule.
Tries what? Do what with universes?
Excuse me, I thought it's like, okay, nothing, it doesn't.
No, it's simply
Has type.
predicative, non-cumulative.
Okay.
This thing exactly says that it's not cumulative universes, and all of them are predicative. So nothing here at all.
Okay.
Very simplistic. Not even sigma types here, just pi types, and no identity. So it's half kind of semi-dependent type system. Well, for the comparison with this stuff, I don't know. Hard to say which is simpler. And again, claim here that this thing is actually totally syntax driven and algorithmic in that sense, or as a fact. And that's totally the very last slide. I don't have anything more to say about the slides. At least backed by slides. Any discussion? Comments from the audience? If there are no comments, suggestions, corrections, or anything, I guess we will have to stop the recording. Yep, Nikolai, please.
Well, I don't know why, but it recalls me very much a paper that I read many years ago. Proofs about folklore, led polymorphic type inference algorithm by Lee and E. Basically, it is about bidirectional type inference for instead of W system. W system. I cannot say anything more. But just that it recalls me. So I just sent you a link to the paper. Okay.
Okay. Well, speaking about these bidirectional ideas and kind of history, well, I guess the main reference, again, this survey, though I don't exactly remember where I read that, or yeah, there check the Proof of Citizens Stack Exchange site, and that question answer I linked on my third slide for some discussion. Again, kind of idea is folklore. The seminal paper, kind of the one that popularized that is that one, local type inference, due to okay, I already forgot the name of both authors. Benjamin Pierce and someone, Turner or someone, sorry, can't recall the second one. Though they refer kind of prior art, yes, some prior systems, and yeah, again, there were developments for calculus of constructions. I believe the authors presented essentially bidirectional system, by they just didn't call it bidirectional. So the ideas were kind of floating, and the thing is kind of folklore. It's hard or impossible to trace to a single source.
Very true, very true. But I just said that I am not a professional in this topic. Maybe it is the only paper that I read approximately 20 years ago.
Okay. Yeah, thanks.
Nevertheless, I provided link. Maybe it will help somehow, at least from historical point of view. Okay, okay, Narai, thank you.
Thanks. Other interesting comments or objections or something? Like going 5, 4, 3, 2, 1. All right then. Thanks for sticking with me for so long. And thanks for watching. If you're watching that the recording on YouTube or somewhere till this very moment. Thank you very much. And
Thank you, Alexander.
Wrapping up.
Yeah, thank you.
You're welcome. Thanks for having me. Yeah, bye.
Goodbye.
Thanks. Bye.